Yeah. Yeah, I want people to see like that. Very part of it. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good to see everybody. We are it's getting close to spring break, and so we just have this week and then next week, and then we'll be on spring break. So I think that's what everyone hopefully is looking forward to. I'm looking forward to that. Okay. So lecture for today is we're going to continue talking about our theorems for vector calculus. And so today we're going to go over Green's theorem. That's going to be the main thing that we talk about. So we're going to do an example with that, how to use it. That'll be useful for your guys' homework assignment, problem 4 on homework 4. And then, I think for the second half of the day, we'll probably start talking about surface integrals, but I'm not sure how far we're going to get. But we'll get as far as we can before we have to stop for today. Okay. All right. So other announcements. So remember, homework 4 is out there, so that is due this Sunday. I gave you guys a little bit extra time because I did expect that we're going to be talking about divergence theorem all the way up until Thursday. So right now you're not going to be able to do the last problem just yet. But as of right now, you should be able to do the first two problems 2 and problem 3, and after today you'll be able to do problem 4 as well. And then after Thursday, you can do problem 5. So make sure you're just kind of working on that homework set. It is a little bit lengthy, just because there's a lot that we've covered over the last couple of weeks, but just make sure you're kind of getting on top of that. Okay. Okay. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. Okay. So we're going to start today talking about Green's theorem. So Green's theorem is quite a famous theorem in applied mathematics. I think it's most famously used in fluid mechanics, although it does have applications in electromagnetics. Anything that requires vector fields or scalar fields to some degree. Okay. Okay. So what's the setup for this theorem? So at its core, Green's theorem is what I call kind of a transformation theorem. And so it basically allows you to transform one type of integral into another type of integral. In particular, for Green's theorem, we're going to be looking at line integrals and then transforming that into a double integral. Okay. Which is really kind of convenient. And so, I think you'll probably see Green's theorem in some of your other courses. And mostly Green's theorem is presented as a way to kind of motivate kind of the physical interpretations or the physical, background of some of the terms in your equations. And, that's traditionally how it's introduced. But for this class, we're going to use it kind of as a tool of convenience, because oftentimes, one of these integrals, either the line integral or the double integral, are going to be easier to compute. Okay. And so essentially what this allows us to do is it allows us to pick, which of these integrals that we want to do to solve a problem. All right, because in most cases, there's going to be one way to solve a problem that's going to be much easier than the others. And when you're kind of first introduced to this, it may not be immediately clear which is going to be easier. But as you're going to do more and more of these, it becomes more clear which way is easier than the other. Okay. Okay. And I will say that for a lot of cases, the criteria or the way that you determine which is easier than not is going to depend on the domain or kind of the area in which you are performing this integral. Okay, so I'll give you some quick examples here. And then through these examples, we'll kind of review a little bit what it means to take a line integral, because that was kind of the subject of our lecture last Thursday. Okay, let's look at a square region. Okay, so let's say that we have a XY plane here. Okay. And let's say that we have a square region that kind of looks like this. Okay. Where maybe the X coordinates for the domain go between, I don't know, 1 and 4. And the Y coordinates go between 2 and 5. Okay. So each side of the square is length 3, and it just take up a different portion of the XY. Okay. Okay. So let's see what this would look like if we wanted to integrate over this region with a double integral. Okay, so with the double integral, we have kind of a nice square region here. It's very much bound between x is equal to 1 and x is equal to 4, and y is equal to 2 and y is equal to 5. Okay. So we have 1 is less than or equal to x, which is less than or equal to 4, and then 2 is less than or equal to y, less than or equal to 5. Okay. So a square domain like this, because our x and y bounds here are pure constants, the double integral is actually very convenient to do here. And so all we have to do is we have to do double integral from, and it doesn't matter which order you do it, but let's integrate over x first. Okay, so we're going to go from 1 to 4 for x and 2 to 5 for y. Okay. We have our integrand, and so our integrand can be some function. Okay. dx, dy. Okay. So in this case, for a square domain, it's very natural to think of it in terms of double integrals, because it's you're integrating over that entire region, and because it's square, x and y has very clearly defined upper bounds and lower bounds. Okay. Okay. If you look at the line integral, though, so line integrals in this case is actually going to be very difficult to do. And so the way a line integral works is that you have to parameterize the curve that goes around your domain, okay? And because we have sharp corners on the square here, we have to do kind of a piecewise parameterized curve. So we can't have just one curve that goes around the entire domain because of the sharp corners, right? So we have to actually do this line integral in 4 different segments. Okay. So we have segment, I'm just gonna start from the bottom. So we have segment 1, segment 2, segment 3, segment 4. Okay. And so if we wanted to do a line integral around this region, we have to do 4 separate integrals, one for each segment of the square. Right. So we're going to have line integral of segment 1 ds plus line integral on segment 2 ds plus line integral on segment 3 ds plus line integral on segment 4 ds. Okay. Because remember, what's required for a line integral is that you have to have a parameterized version of your curve on each of those segments. That means each of these integrals, each of these 4 integrals here, have to have a separate curve parameterization. Okay. Which, you know, you can do that, and so that's it's not the worst thing in the world, but at the same time, it's going to be very time consuming and kind of very annoying to do this. Not only do you need to do 4 separate parameterizations, 4 separate integrals, but that's going to be 4 separate integrands that you have to, you know, integrate as well, and those are all going to change depending on the parameterization. So, you know, in this case, you know, a double integral is just a lot more straightforward in this kind of, you know, in this kind of situation. Because all you need for a double integral is just the upper and lower bounds for each of the x and y coordinates, which is very natural to do with a square. Okay. So for, you know, for the problems that we're going to do today and the problems that you're going to see in the homework, you're mostly going to look at the domain in which you're integrating on, and you're going to decide based on that domain which is easier to do or not. Okay. And by the way, there's no right or wrong decision with this. You know, all the integrals that you're going to do on the homeworks and all the integrals we're going to do today, you can do them either way. And so if you end up choosing the more difficult way, you know, it's not bad. It's just that, you know, just there's one way that was kind of easier than the other. And so just kind of take it as kind of a learning kind of experience. Okay, any questions on this so far? Okay. All right, so let me give you an example of a case which is easier to do with a line integral, which is a circle. And in fact, I think the example that we're going to do today is actually on a circle. Yes. Okay. Okay, so a circle looks something like this. Okay. So let's talk about what we need to do to integrate this with a line integral, with a double integral first. Okay, so with the double integral, you know, we're gonna be integrating across this entire area. So we need to cover everything that's inside the circle, right? The problem is, you know, with the circle, we have all these curved edges, and so we don't have a strict upper and lower bound for x or y. Okay. So what we do have is that, you know, we know for a circle in terms of xy coordinates, right? The formula for a circle is the following. So we have x squared plus y squared is equal to r squared, where r is the radius of that circle. Okay. We can solve for one of these, and so let's say that we solve for y, right? And so we get y is equal to square root r squared minus x squared. So all I did was just I manipulated the equation of the circle and then solved for y in that case. Okay. Okay, so if you were to do this with a double integral, okay. Remember, with a double integral, the way these work is that you're integrating over each coordinate kind of separately. So you're integrating over x over y first, and then you're going to integrate over x. Okay. Okay, so let's do the integration over y first, right? So y is going to be our inner integral in this case. Okay. So y doesn't actually go to any fixed value here, unlike the square. So y actually goes from 0 actually to this expression here. And so when we integrate over y, we're going to go from 0 to square root r squared minus x squared. So you have kind of a variable in your integram there. And then your integral over x is going to be between 0 and r. So again, it's not the worst thing in the world, but whenever you have variables in your integration bounds, it's never a pleasant integrating experience. You could argue that there's no experience that's a pleasant integrating experience, but having variables in your integration bounds is especially not pleasant, because then it turns your math into quite a mess. Okay. So again, you can do this, but in this case, a line integral might be a little bit better to do. Okay. Because with the line integral, you can have just one curve, one parameterized curve that goes around the exterior of the circle. So there's no need to kind of break it off like there was in the square, because there's no sharp points. Right? Okay. And so we can have kind of one smooth curve here. So we kind of follow the red arrows here, right? Right. We can have kind of one smooth curve that goes around that entire exterior there. So in this case, our line integral, okay, will just be around that circle ds. So in this case, you're just doing one integral. You have to parameterize the curve, and so some people really don't like parameterizing the curve. So I've had students in the past they just always do the double integral, just because that's kind of what you've learned before. Line integrals are kind of new, and that's fine. You can do that. But I would in this case I would make the argument that the line integral is a little bit more convenient, just because you can do it all kind of in one shot. Okay, so these are kind of the two most common examples, and so I think most of the problems that we're going to do is either a circle or a rectangle of some kind. But once you start to get used to kind of these types of integrals, and you start to get a preference for one using the other, then you can use Green's theorem to kind of convert between one or the other. Okay. Any questions on this so far? Okay. All right, so now that we have a sense of kind of what the domains actually start to look like, and kind of which ones might be easier, let's actually talk about Green's theorem. Okay. Now, I've been talking about Green's theorem today as if it's kind of this magic pill that you can use to transform one to the other. But that's not 100% true. So, Green's theorem, the way it works is that your integral has to be of kind of a very specific form in order for you to perform this transformation. Okay. Okay. So in order to start, we have to have some kind of vector field that we're integrating. So we're going to let F be our vector field. So remember, a vector field is a multivariable function that has a vector value quantity at every single coordinate x and y. Okay. And we're going to assume that F1 and F2 are the components of this vector field. Okay. And of course, right now we're sticking to 2 dimensions just to kind of make things a little bit simple. Okay. Okay. And so with that definition out of the way, let's present Green's theorem. And so there's a couple different forms of this, okay? And so the first form, I'll give you kind of the cleanest looking form first. And so one form of Green's theorem basically says that if we take the double integral over a region R, okay? So this R here, this is our region of integration. And again, that's going to depend on the problem. So that's going to depend on whether it's going to be a square or a circle, depends on the region that's given to you in the problem. Okay. Green's theorem basically says that if you're taking the double integral of the curl of the vector field, okay, right? Remember last time on last Thursday, we talked about curl. Okay. So the curl, member is just the nabla crossed together with the vector field. Okay. This is going to be equal to a line integral, okay, a line integral around the boundary of that region R, right? And so what we can say here is that this is the region is given by delta R, right? So this curve right here is the boundary over the same region R. It's a boundary around. Okay. And the integrand in this case is the vector field F dot product with the curve around the integration bound. So we're basically taking the line integral of the vector field F around that parametrized curve. Okay. All right, so that's Green's theorem for you. So Green's theorem is that it's a connection between the double integral of the curl of a vector field together with the line integral of that same vector field around the boundary of that region. Okay. Okay, so that's kind of the clean version of Green's theorem. So this is the one that's normally presented because it looks clean. But it's not that useful for plugging into formulas. So let me actually give you that form here. Okay. So another version of Green's theorem that you'll probably use in your problems looks like the following. Okay. So we have double integral over the region R. And so I'm actually going to write out the curl of the vector field in 2D. And so this is going to be partial F2 partial X minus partial F1 partial Y dx dy. And that's equal to line integral around the boundary of the region R of F1 dx plus F2 dy. Okay. So this form is a little bit more useful because this kind of gives you things that you can kind of plug in a bit more directly, as opposed to computing the curl and things like that. Okay. Okay, so the next thing we're going to do is we're going to do an example to kind of show you. We're going to compute, both integrals. So we're going to prove Green's theorem for a simple case, and you'll see that both of these integrals, when we compute them, are going to give us the exact same thing. But what you're going to see is that one integral is going to be much easier to compute than the other. Okay. All right. Any questions on this? Okay. All right. So let's do an example to kind of illustrate how this works. Okay. So in this case, we're going to verify Green's theorem. So we need a vector field. So let's let F be defined as the following. F of X and Y, right? Since we're in 2D, F here is going to have two components. We have F1 and F2. So F1 in this case is going to be y squared minus 7y. And F2 is going to be 2xy plus 2x. Okay. So this here is F1. This here is F2. Okay. The two components of our vector field F. Okay. And so the region of our integration here. So, when you're doing these multidimensional integrals, you need to know the region as well. And so the region of this integral is going to be a circle of radius 1 centered at the origin. Okay. And so our integration region looks like the following. If x, y, we have a circle, and its radius is equal to 1. Okay. Okay, so we want to compute kind of both sides of Green's theorem in this case. Okay, so let's do kind of one by one. So let's start with the double integral side. And so our double integral side is going to be double integral around the region R of partial F1, or excuse me, partial F2, partial X, minus partial F1, partial Y, dx, dy. Okay. And so we need to do that for our region R. Okay. Okay, so first thing I'm going to do is I'm going to compute the integrand there. So partial F2, partial X. Okay. Okay. So partial F2, partial X, that is, so our F2 here is 2xy plus 2x. And so we take the derivative of that with respect to x, we get 2y plus 2. Okay. And then we're going to take partial F1, partial y. So partial F1, partial y, we get derivative of y squared is 2y minus 7y. That's minus 7. We're going to subtract these two things. Okay. So this, of course, is going to simplify. And so we have the two y's are going to cancel out. And we have 2 minus 7. So that's going to give us a positive 9. Okay. And so we have just integration of a constant here, which is quite nice, because now that constant can just kind of factor out. So we have 9 double integral around the region R, dx, dy. And so we have double integral across a region of just 1. And so this is a very special integral here. And so when you have the integral of just 1, this ends up being just the area of that region. And so we have area of a circle. Area of this circle is pi r squared. R is equal to 1. And so this whole integration here is going to be 9 times pi. Okay, that's kind of the easy way to do it. But then, but at the beginning of class, we kind of made this whole argument of, doing the double integral of a circle is a little bit inconvenient. So actually, let me kind of show you what that actually looks like, right? So we know what this integral should be. We know this integral here should be pi. But let's kind of see that happen through transformation of this integral. Okay, so if we were to actually do this integration here, our integration bounds would look like the following. So in this case, since we're doing the x integration first, we have to parameterize the circle in terms of x, right? Because we know the formula for the circle is going to be x squared plus y squared is equal to 1, right? If we solve this for x, then we get x is equal to square root 1 minus y squared. Okay, and so our integration in that case would be our y is going to go between 0 and 1. And our x integral here is going to be from 0 to square root 1 minus y squared dx dy. Okay. Okay. I'm trying to decide, I'm looking at the timer here. And so, if you carry out this integral here, you would get simply just the area of the circle, and then that will give you kind of the that answer pi. But it is 430. So I do want to move on to the line integral, because I think that takes a bit more practice. But that's essentially how you would do this integral, if your integrand wasn't so simple in this case. And so our integrand in this case ended up being simple, and so we can just plug in just the area of that region. But if you did want to actually plug in the bounds, this is kind of how you. Okay, so let's do the line integral side now. Okay. So for the line integral side, we're going to take a line integral around the circular region around the domain. Okay. So in order to do that, we need to parameterize the curve that goes around the region, around the circle. Okay. Okay, so to do this, to get a parameterized curve, you need to have some function r of t. Okay. Where t there is your kind of one parameter that you need to do, okay, to parameterize the curve. And then as part of the parameterization, you're going to have a function x of t and a function y of t. Okay. And the important thing is that they're all going to be a function of the same parameter t. Okay, so for a circle, remember we talked about this last time. A circle kind of has a very simple parameterization. And so for the x coordinate, we're going to go cosine t. And for the y coordinate, we're going to go sine of t. Okay. And so if you plot this from t is equal from 0 to 2 pi, so that's going to be one full rotation around the circle. That's going to take you on a path around the circle, right? So this describes the x coordinate and the y coordinate, of that circle. Okay, so what you're going to need here is you're going to need both. You're going to need the derivative of this. Okay, so you're going to need the tangent to this curve. So we need dr dt. Okay. So remember, the way we get this is we're just going to take the derivative of each component, dx dt and dy dt. Okay, and so let's take each component here, and so that's going to be minus sine of t, cosine of t. And then the next thing that we need is we need to parameterize our vector field in terms of this path. Okay, so remember we did this was kind of the last example we did last Thursday. So we're going to take our vector field, and everywhere we see x and y, we're going to plug in our parameterization. Okay? So if we go back to the problem here, we have our vector field f of x and y is equal to y squared minus 7y, comma, 2xy plus 2x. Okay. Okay, so let's plug in our parameterization. So everywhere that we see y, we're going to plug in sine of t, right? Because that's what our parameterization kind of defines for us, right? So y is going to be here as well. And then everywhere that we see x, we're going to plug in cosine of t. Okay. Okay, so we plug all that in, we get y squared, which is going to be sine squared of t minus 7 sine of t, okay, comma, 2xy, so that's 2 cosine t, sine t, plus 2 cosine of t. Okay. And so to perform the line integral, we're going to take this quantity and dot product it with the tangent of the curve. And so I'm not making a great argument for the line integral. Normally this is easier than it is, but you know, sometimes this is easier than the double integral. Okay? Okay, so we're going to take our f here, which has been parameterized in terms of t, and we're going to take the dot product with that with the tangent of the curve, or dr dt. Okay. And so if you do that, if you do this symbolically first, this is going to be f1 times dx dt plus f2 dy dt. Okay. Right, which is exactly kind of what we have in the integrand of our Green's theorem, kind of in the more simplified version, or the version that's more easy to plug in. Okay. So let's go ahead and plug in for all of these, because we have f1, we have f2, and we have the tangent of our curve, dx dt and dy dt. Okay, and so we plug these in, and what we get is f1, which is sine squared of t minus 7 sine of t multiplied by dx dt, and so that's going to be a minus sine of t plus f2. f2 is 2 cosine of t sine of t plus 2 cosine of t multiplied by dy dt, which is cosine of t. Okay, so let's go ahead and multiply these through. And so we're going to get kind of a beast of an integrand here. Okay. And so we multiply these through, we get minus sine cubed of t minus 7 sine squared of t plus 2 cosine squared of t sine of t plus 2 cosine squared of t. Okay. Yeah.
I'm pretty sure the minus 7 sine squared t should be positive.
It should, yes, thank you. All right, so that is our integrand. And so to perform the line integral, we need to make one full rotation around the circle. So we're going to integrate from 0 to 2 pi dt. So of course, this is not a pleasant integral to do. And so this is where you'd have to kind of pull out a lot of the trig identities, so a lot of the double angle formulas, maybe some trig identities, things like that. Okay. So one thing for sure is that you can combine, right? So we have a 7 sine squared of t and a 2 cosine squared of t. And so you can kind of combine these together into 5 sine squared of t plus 2 sine squared of t plus 2 cosine squared of t. Okay. We know one of the most famous kind of trig identities, the one that's my favorite one, the one that's easiest to use, is that sine squared plus cosine squared is equal to 1. And so this is going to combine to 2. Okay. Right, so that's one way that you can at least kind of simplify it a little bit. So the 5 came from, I just separated these two out. So I separated the 7 sine squared of t into 5 sine squared of t plus 2 sine squared of t. So I did that just so I can combine it together with this 2 cosine squared of t. Yeah. Mm-hmm. Yeah, so I'm not going to go through the trig identities for everything here. Just know that you can evaluate this integral. We're kind of in a similar position that we were in kind of at the end of class on Thursday. But if you utilize your trig identities here, what you'll find out is that this integral here is equal to 9 times pi. Okay. Okay, so I didn't do a great job of making the argument for a line integral, right? So most of the time, the double integral is probably going to be a bit easier. Just because with the line integral, especially with the circular domains, you're going to end up with a lot of trig terms if you trig it in. Okay. And if you compare that to the result that we got from the double integral, kind of way up here, right? I didn't actually write it out, right? We have 9 multiplied by the area of that region, which is pi. And so that just ends up being 9 pi. Okay. So through this example here, we can see that in both cases, we end up with the same result, right? So whether we did the double integral or the line integral, we end up with the same answer. Okay. And so in this situation, it's you don't need to do both. unless the problem asks you to do both. And so, if you were in the situation where you were asked to compute this line integral around the region, you could instead compute the double integral and get the same result through Green's theorem. So again, most of the time it's going to be the double integral, but it may surprise you. So sometimes you'll have a situation with a line integral. It's a little bit easier to compute. So maybe you don't have as many kind of trig identities to do in the line integral. Okay, so it's going to depend on your domain. It's going to depend on your integrand. And so try. It wouldn't hurt to kind of try these integrals kind of both ways and kind of see which one is more convenient. Okay. Any questions on this so far? Okay, so before we move on to surface integrals, let's talk a bit about kind of the physical intuition behind the Green's theorem. Because when you're talking about these kind of integral and calculus theorems, it's very easy to kind of get buried in the weeds and the details and everything. And so it's sometimes it gets a little bit lost in the sauce in terms of what these theorems actually mean and what they actually can, how they can actually contribute to our physical understanding of the world. Okay. So, both for this theorem, and both for Green's theorem and the divergence theorem, which is what we're going to talk about on Thursday, I did want to spend a little bit of time talking about the physical intuition behind them so that you can kind of better understand what these theorems are about and what they're trying to explain. Okay. Okay. So let's write out Green's theorem again. So Green's theorem, the double integral side looks like the curl of the vector field F dA, and that's equal to over a region R, forgot that, okay. And that's going to be equal to the line integral around that same region R of the same vector field but a line integral around that region, okay? And so Green's theorem is basically telling us that both of these integrals here are equivalent to each other, right? So what does that actually mean? So let's start with the left side. Okay. So this left side, is actually kind of very intentional in terms of how it's kind of written out. And so on the one hand, we have, let's start from the inside and go out. So on the inside, we have the curl of the vector field F. And remember, we talked about the curl last Thursday in terms of what that means. So the curl basically is a quantity that tells you how much swirling there is in the vector field F. Okay. Because remember, for any given vector field F, we have basically a vector quantity that's associated with every XY coordinate. Okay. And so if those vector quantities are kind of, going around in a circle or they tend to swirl something, that's going to show up in the curl of the vector field. Okay. Okay. But the curl is actually very interesting in terms of how it's defined, because when you take the curl of a vector field, you get another, you you get another vector field in response, right? And so when you take the curl, it's very much a what I call kind of a local computation, where it tells you kind of a locally, how much swirling there is at a specific XY location. Okay, and the curl is going to give you a different answer when you move to different X and Y locations. So it doesn't tell you the amount of swirling there is overall in the vector field, but it will tell you how much swirling there is at this point versus that point, right? It's very much a local computation, as is most the case when you take derivative-based quantities. Okay, and so for example, let me kind of draw a vector field here. Right. So remember, vector field is going to look something like this, where the arrows are going to be pointing in a different direction at every single spot. Okay. And so when you compute the curl, right, the curl is going to tell you how much swirling there is here, right? And that may be different compared to how much swirling there is over here, right? So it's a very point-by-point quantity. Okay. But we're not just computing the curl here, right? So in Green's theorem, we're actually taking the double integral of the curl within a given region, right? And so let's say we have a region R right here. Okay, so this is our region R. By integrating the curl around in this region R, remember, kind of one way for us to interpret the integral is that an integral is kind of almost like a summation of everything that's inside that region, right? So in other words, what we're saying is the double integral is going to sum up all of the curls that are occurring within that one region. So that quantity, that double integral, is kind of almost like the total amount of swirling or the total amount of rotation that's occurring within that region R. Okay. So that's how you can kind of interpret kind of the left-hand side of Green's theorem, is that you're computing the curl, it's a location by location local quantity, but by taking the integral, you're summing up all of the swirling that occurs there. And so for a given region, you're gonna get just one answer, one number for how much swirling or how much rotation is happening within that region. Okay. And that's very useful in a lot of cases, mostly fluid mechanics. So that's a lot of times you're interested in vorticity. Which is how much rotation is occurring in a flow field within a given region. Okay. Okay, so that's the double integral side. So now let's look at the line integral. Okay. Okay, so the key point to kind of talk about with the line integral, and this is true for all line integrals, is this dot product quantity. Okay. So here we're taking the dot product between the vector field F and the tangent of the parametrized curve dr dt. So what is the interpretation of a dot product? Well, there's lots of interpretations of the dot product, but let's focus on just kind of one important one, right? And so one way to interpret the dot product is that, if you look at kind of the relative orientation of the two vectors you're taking the dot product of, the dot product will kind of tell you how much those two vectors are aligned with one another. Okay. So if those two vectors are parallel to each other, that's going to give you a high number. But in the worst case, if your two vectors are perpendicular, right, we know that the dot product between two vectors that are perpendicular are going to give you 0. Okay. Okay, so that dot product tells you basically how well your vector field is aligned with your path. Okay. Okay, so what do we know about this path? And so this path is actually very interesting. So this path here goes around this region R, right? Right? That's how Green's theorem is defined. So, we have to integrate around that same boundary that's in the doubling. Okay. Now I underlined the word around because that's kind of the operative keyword, because when you take a line integral around a closed region, right? That means your starting and ending point are the same, right? So it doesn't really matter where you start, right? But you're going to travel around this domain and you're going to end up at the same place. Okay. And so this is a closed curve. And so what's unique about a closed curve? So if you start and end in the same location, right? And you traveled more than 0, right? And so, you didn't just hop in place and just end up at the same place. You actually traveled around a bit and came back, right? You're going to end up walking in a circle to some degree, right? And so it doesn't have to be a perfect circle. You may walk in a square, but you're going to walk in a circular path, right? So usually there's going to be some counterclockwise or clockwise direction to your movement, right? There's going to be a center of rotation because you have to come back to the same place, right? So it has to be circular because it has to be a closed path. Right? So you have to come back where you start. Okay, so let's combine these two thoughts here. And so let's combine the fact that we know our path is going to be circular to some degree, right? So there's going to be some rotation. And let's combine the fact that we are taking the dot product between our vector f and this kind of circular path, okay? And so what the line integral is basically telling us here is it's basically telling us how well this vector field f is aligned with this circular path, okay? And it's going to be summing that up around the entire path of that path. Okay. So what that tells us is that if the vector field f has any kind of rotation, right, overall, then this line integral is going to pick it up because this line integral, the path is going in a circle, and if we see how much f aligns with that circle and adding that up, that means that line integral is going to tell us how much total rotation f is doing around that path. because again, the path is circular, okay? So if you kind of compare that kind of physical kind of conclusion for the line integral and compare that to the conclusion that we got from the double integral, right? These two things that I've circled here are kind of telling us the same thing, except in somewhat different forms, right? And so on the one hand, we're taking all the little tiny rotations and summing them up with the double integral. On the other hand, we're just going around the boundary. But since the boundary is circular, right? And we're finding out how much F aligns with that circular path and summing that up. So these two things, Green's theorem basically tells us that these two things are equivalent to each other. Okay, so these two things are the same. Okay. And mathematically, that's exactly kind of what Green's theorem tells us as well. Okay. So, whether you're taking the line integral around a closed region or you're taking a double integral of all the curls within that region, you end up with the same thing. And so you might as well just choose one, which is kind of more convenient to compute than the other. Okay. Okay, so I wanted to make sure I explained that today because I think this is kind of, the calculations are important for these things, but if I'm being kind of perfectly honest with you guys, even in your other classes, you're probably not going to be doing too many double integrals or line integrals. So I think it's more important that you guys kind of, really kind of understand this physical interpretation, just so that you can kind of understand and appreciate kind of the theorems, and the concepts that you're going to see in your other engineering courses. All right, any questions on this here? Okay. All right, so for the last 15 minutes today, I did want to introduce the concept of a surface integral, and then we'll finish that up on Thursday with divergence theorem. Okay. Okay. So what is a surface integral? So a surface integral is something that you're going to see, actually quite common in your other classes. Most specifically, I keep bringing up fluid mechanics, but fluid mechanics is very much, it's very calculus based. You're also going to see it in heat transfer, electromagnetics, solid mechanics, and so surface integrals are something that's very okay. And so I think the best way or the easiest way that I can describe a surface integral is that it's a generalization of a double integral to three-dimensional space. Okay. All right, so we just got done talking about double integrals, and so double integral, looks something like this. Okay. But all the double integrals that we've been doing have been pretty much constrained to just the XY plane. But it's possible in three-dimensional space to have, two-dimensional surfaces, right? And these two-dimensional surfaces could be curved as well, okay? And so, for example, let's say that we have a curved surface, that's going to be kind of like the surface of a cylinder. Right? And so we draw a cylinder here. The cylinder itself is a three-dimensional object, right? But if you just took the surface of that cylinder, just kind of the outer shell, that itself is a two-dimensional surface. It's just wrapped in three-dimensional space. Okay. So the kind of the way that I always like to visualize this is like, think about the wrapping paper. So if you had a cylindrical gift that you were to give to somebody, and you were to wrap it in wrapping paper, the wrapping paper itself, that would be kind of the surface that you would use for a surface in it, right? So technically it's in three-dimensional space, but since the wrapping paper is so thin, you know, it's effectively a two-dimensional integral. Okay. Okay. So what do we need to compute a surface integral? Well, let's kind of take some inspiration from our line integrals from before, right? So just like in our line integrals, we need to have some kind of parameterization of our curve, or in this case, a parameterization of our surface. Okay. Okay. And so I'm going to use the symbol R very similarly to our parameterized curves. But since we're parameterizing a two-dimensional surface, we need two parameters. So it's not just going to be T anymore. So I'm going to use U and V. Okay. So it's going to be R of U and V. Okay. And since we're in three-dimensional space, we need to have three components to our parameterized surface. So an X component, a Y component, and a Z component. We have X of U and V, Y of U and V, and Z of U and V. All right, so U and V here, you can consider them to be kind of the surface coordinates. Okay. And so by plugging a pair of surface coordinates into the parameterized surface here, it's going to tell you the X, Y, Z location of where you are on that surface, right? And so you can think of the parameterized surface as kind of a change of variables between the surface coordinates U and V and the traditional Cartesian coordinates X, Y, and Z. Okay. Okay, but I think the easiest way to kind of show you is with an example. So let's do a cylinder first. Okay. So if we look at the parameterization of a cylinder of radius A, remember we just want the surface around that cylinder. Okay. So in this case, our parameterization R of U and V is equal to A cosine of U, A sine of U, okay, and V. Okay, where this first component here, this is our X of U and V. This is our Y of U and V. And this right here is our Z of U and V. Okay. Okay. So I like this cylinder here just because it's a bit easier to kind of visualize, right? Because when you plug in a certain value for U and V, it's going to give you a point on the exterior of your cylinder. Okay. So for example, So this is an example within the example. Okay, so let's say that we plug in a value of u is equal to pi and v is equal to 3. Okay. Right, so those are your surface coordinates, right? So let's see where we are on the cylinder in terms of x, y, z with these coordinates here. Okay. Okay. So r of pi and 3, right? X coordinate here is going to be a times cosine pi. Cosine pi is a -1, so it's going to be a minus a. Okay. Next, we have a times sine of u, and since u is pi here, sine of pi is just 0, so this can be 0. Okay. And then v is 3, and so that's going to be our z coordinate. So that's going to be 3. Okay. And so if we plot that out, let me do x, y, and z. Okay. So let's see. So our x coordinate here is minus a, and our z component here is 3. Right? And so this is going to be our coordinate here. So this right here is minus a, and this right here is 3. Okay. And if you draw the cylinder here, right? Our cylinder kind of looks like the following. Right? So in this case, it's a cylinder that goes up in the z direction. And this point that we defined here, this pi comma 3, that sits on the exterior of the cylinder, just kind of on the left side. Okay. All right, any questions on that example here? Okay, one more very quick example, just because we're going to use it on Thursday. But let me give you the parameterization for a sphere. Again, we're looking at the surface around the sphere, so we're not looking into the body of the sphere itself, just the exterior surface. Okay. Okay, so let's say that our sphere again has a radius a. Okay. So a is just some generic number. Okay. And so our parameterization for this, r of u and v, is equal to. So x value here is a times cosine of v times cosine of u. Okay. Y coordinate is a times cosine of v multiplied by sine of u. Okay. And the z component is just a sine of v. So if you plug in certain values for u and v here are kind of the spherical coordinates, and so they go between 0 and 2 pi. That's going to give you any point on the exterior of the sphere. Okay. And so our sphere, looks something like this. Okay. And the radius is a. Okay. Okay. So when we come back to class on Thursday, we'll start to use these parameterizations on surface integral. So we'll talk about that, how to compute those, or more like how we're never going to compute a surface integral because it's never convenient. But we'll talk about the physical interpretation of a surface integral, and then we'll talk about the divergence theorem, which lets you convert these surface integrals into something that's more convenient, which is usually a triple. Okay. All right. So thank you guys for coming today. Hope you guys enjoy the rest of your day, and I will see you guys on Thursday.
Oh, really? Oh, yeah. 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 That's what I saw. Checked in. Like by yourself, when you like this, there's a key. It's not anybody that's like, he's like, do it, this is kind of very chatty. He would go up there and look at it. I just take a picture. But he was like, yeah. I love Facebook.